So good morning, everyone, and welcome to the second episode of Axiom Optics Microscopy webinar series. I'm Vincent Renaud, and here should also be Peter Drent, Sales and Marketing Manager at Confocal.nl and also founder of Confocal.nl, and Jeroen Kool, Product Application Specialist at Confocal.nl, and myself, Vincent Renaud, Sales Manager at Axiom Optics. I'm really happy to welcome you for this second webinar. It's going to be very exciting. We are introducing the Rescan Confocal Microscope 2 to the US market. So I hope you are ready. Let's start with today's outline. So I'm going to start with a very quick introduction of Axiom Optics and Confocal.nl. And then I'm going to introduce the RCM2. Sorry, I'm going to give the hand to Peter, who is going to introduce the RCM2 and give you some application examples and systems highlights. And then Jeroen Kool is going to do a live demo of the RCM2, and we're going to finish with a question and answers. This gives me the opportunity to tell you that there is a chat window on the right side of this webinar Jan window. So if you have any questions during the webinar, feel free to write them down, and we will answer them at the end of this webinar during the question and answer session. So I'll start with the introduction of Axiom Optics. Axiom Optics is a company specializing in high-end optical instrumentation, and we have a microscopy division with 3 people. Philippe Clemenceau, who is a co-founder of Axiom Optics and who is based on the East Coast. Lauren Vincent, who has been organizing this webinar and is our marketing specialist, and myself. For the microscopy division, we offer high-end systems. Of course, the Rescan Confocal microscope, which is a laser scanning confocal system that you're going to learn more about today. But we also offer the fluorescence lifetime imaging system from Lambert Instrument, which is a camera-based system. We also have different systems for single molecule localization microscopy, so super resolution microscopy, from Abelite and from Imagine Optic using adaptive optics. And finally, we also offer the optical tweezers and force measurement platform from Impedex. With that said, I'm going to give the hand to Peter, who is going to give you an introduction about RCM2.
Okay, so let's take it from here. I saw already some familiar people in the audience, so of course everybody in the audience, welcome, and join me in saying finally here. You get some movie now played by Jeroen, which is the teaser movie we made for the introduction of RCM2. We discovered that in the digital world, there are new opportunities for RCM.
So, we entered this world with a clever designed new product, the RCM2.
With this digital and sensitive confocal imaging system, you can see more cells at full resolution at once.
So, stay comfortable and continue to use your favorite software while improving your imaging experience.
You're still muted. You're still muted, Peter.
Oh, I'm sorry. Jeroen always unmutes me. So I'm sorry. This teaser movie, we bombarded social media. And why we made this team movie? Because it has 4 chapters: digital, see more, clever design, and software. And in these 4 chapters, I want to explain you all the features and benefits of the RCM2. Let's go to the first one. Before we go there, I want to explain RCM, because maybe some of you are not so familiar with RCM as we are yet. So here you see the drawing of a regular confocal microscope, which has a laser, a microscope, a scanning mirror set, then you see the pinhole in front of the PMT. So the PMT measures the average intensity over the pinhole. So what we did is we take away the PMT. The pinhole is there, the PMT is gone, and we placed a second scanning mirror set in the box. And that second scanning mirror set writes the information on the camera. So we have a scanner that reads the information from the microscope, and we have a rescanner that writes the information on the camera. So this is the technology invention. I always call it technology invention because why? We wanted to use the most sensitive detector, which is at this moment the scientific CMOS sensor. The scientific invention I will explain in the next slide. In 4 scenes. Scene 1, scanner and rescanner are in sync. So the information that we see is purely written on the rescanner. So this is a regular confocal microscope. So now the invention starts to happening in 2. So now we're going to write the information that we see on twice as large area. So what's going to happen, you see in scene 3, the dot has to move faster on the rescanner. So we have to add a little bit of motion blur. But now, when we scale back in scene 4, the information to the regular size, you can see that also we scale back the dot. We made a sharper image. We improved the resolution with the square root of 2. So what you put in, you get improved out. That's the scientific invention. Next slide. So this is RCM2. What you can see immediately is that the box became a little bit bigger. And that bigger has a reason. What we did, we improved the sizes of the mirrors, of the lenses, and of the scan mirrors. So everything became bigger, and bigger with a reason. With the reason that we also now want to address the lower magnification. And in the lower magnification, you have a bigger beam size. So you need to have some room to allow the beam to maneuver around the scanners. Okay, more about that later. So this is the digital work. I talk about the digital world. And why I want to say we discovered in the digital world there are new opportunities. Because in the analog world, we have a problem. This happens sometimes, not the snow. The snow happens many times, and also in America. But here you can see a typically Dutch situation. You have a bicycle, and the bicycle is actually a rescanning system. You have the front wheel is a scanner, and the back wheel is the rescanner. And you can see in the track that sometimes it happens that the scanner and the rescanner are not in sync. So you can imagine this affects image quality a bit. So we wanted to improve that. And that's why we found digital technology. Here is a screenshot from my iPhone that I took in the first place that we had with the digital scanners. So the digital scanners are programmed to scan a pattern. And this program can be any, and these patterns can be changed any moment. So you see them hopping around. And this has advantages. This is ultra-precise scanning. So to do this, this technology is designed by a company in Belgium, and especially in Flanders, the Dutch-speaking part of Belgium. There's a company called Newson, and they completely changed the concept of scanning mirrors. So normally you have a big magnet, and the big magnet needs lots of current. That's why you need to have big power supplies to manage the turning point of the mirrors. So this company completely changed it. So they changed around the order, and now the electronics is moving around, and the magnet is steady. Also, they put computing power on the scanner. So these scanners now can be programmed, and they execute the program. And in our configuration, they work very nicely because you can say to the rescanner, please follow the scanner. So no extra programming is needed. They are always in sync. With this, we have better precision. Next slide. So what does this ultra-precise scanning, I call it, ultra-precise scanning. So what we do is bidirectional scanning is a standard. All other companies struggle a little bit because you need to have very precise alignment. But in our scanners, it is standard. And this precision of the scanning devices is going to facilitate correlation microscopy a lot. and is also going to help us with precise scanning of regions of interest, multiple regions of interest. And for the academic people around us, I have put this line in here. It maybe enables SIM scanning, because we can program any pattern and we can change any pattern. So maybe some of you are going to work on SIM scanning. Next slide, please. Okay, this is Marilise, operation officer in our company. She talks about clever design. So in the next slide, you can see it's really a totally new product. You know, the bypass mode, we learned from user feedback, I have to say, the knob was regarded to be a little bit difficult to operate. The knob became a lever, okay? Like I said, we don't need a power supply anymore, or at least not a big one. The new power supply is the same size as an iPhone power supply. And because they are digital scanners, they are connected via USB to the PC, so we don't need a control card anymore, which also allows the RCM2 to work on a laptop. And inside, we have a better layout. Maybe most of you will never see that, but for us, it's very important. It makes the RCM2 easier to build and to service. Next slide, please. This is Jeroen. Jeroen is talking about see more at once. So see a larger field of view at full resolution at once. So let's go there. Next slide. A little bit of theory in between. This is stirring some attention on the Confocal list server. The image brightness of an optical system can be always determined as the NA to the power 4 divided by the magnification square 2. So with this mathematics, you can compare lenses. Of course, in the real world, you also have to address the glass type and the coating type. But if you want to compare lenses on the magnification, this is a very nice formula to use. Next slide. And if you go to the Nikon Microscopy U website, they did this calculation in fluorescence for all of their magnifications and just the various NAs. And you can see that they already concluded that 40x is a very nice combination with 1.3 NA. It gives for them the most brightest lens in fluorescence. Okay, so we were then eager to look around, okay, what's available on the market? And we discovered that Nikon and Leica are making 40x 1.3 lenses, but Olympus and Zeiss make 40x 1.4 lenses. And of course, this is something that we really, really like, because based on the formula, 1.4 is 35% brighter. Think about 35%, that's really a lot. Next slide. And now you see 100x, 60x, 40x, you know, the Apo configurations, you know, they all have 1.4 NA. So which means that the resolution of these lenses is all the same, okay? But you can see the 40x is 6 times brighter than the 100x. So if you can digitize all of this information, you know, who needs a higher magnification lens? Okay, next slide. So the advantage of brightness, you know, why we like brightness. We have less noise, we have more signal, which means we can reduce the laser power, which causes less phototoxicity, okay? We now have data sets that were acquired with nanowatts of laser energy. I don't think there is a system in the market that can work with nanowatt. We can. So our cells are happy because of the low laser power. You know, we keep them longer alive. You know, in the introduction, you could see a time lapse of 61 hours of living cells still dividing with virtually no photobleaching over 61 hours. And for us as biologists, it's great because now we have lower magnification with high NA, so we can see many more biology happening in the same view field. Next slide, please. To stimulate or to go further on the discussion that we caused on the Confocal list server, we decided that we have a dedicated webinar to this topic. So this will be on 29th of April at 1 o'clock, European time, Amsterdam time. I'm sorry for you. We will make a replay available. But if you want us to address some topics or you have some questions, please send them ahead of us. We will deal with them during the webinar. And Jeroen will try, as always, to show all the different settings live in the demo. Registration will be via our website. In the next slide, this is a very nice slide for me. Here I wanted to show, okay, RCM2 is a nice confocal microscope. It makes super resolution images, but how else does it fit in the market? And here I want to make a comparison to sim systems. Now we have a company X and a company Y. I cannot name the brands. Maybe they will sue me. Company X can work with 40x, but only with 0.95 NA. To get the resolution they claim is 150 nanometer, they need to use the 100x 1.49 lens. Okay. Look at the field of view and look at the laser power they use. Surely double-digit milliwatts. Company Y, they have a 40x 1.4, but they cannot use that combination in the sim mode. Look at the field of view, look at the resolution, and look at the milliwatts, double-digit milliwatts. Company X uses a Orca Flash 4. Company Y uses a PCO Edge 4.2. And look at it. How does this relate to RCM? We have RCM1, very good system, optimized for 60x and 100x 1.4. Larger field of view, resolution of 120 nanometers. The laser power we used is 85 nanowatts. And we use the Orca Flash 4 camera. Okay. Now RCM2. Yes, we can use 40x 1.4, which gives us a really, really big field of view, 220 by 220 at 120 nanometer resolution. And because the 40x 1.4 combination is so bright, we can even reduce the laser power further. Okay. Now we have data sets acquired at 15 nanowatt. And I said it before, now we have a huge view field. Okay, to digitize that, we need to have pixels and we need to have small pixels. And we found that the PCO Edge 26 is ideal to do that. So we can, according to Nyquist, take all the information of the 40x 1.4 in one image. Okay, makes RCM2 very easy to use, a single image, no reconstruction, no artifacts, and all the 120 nanometer resolution in the view field. Okay, next slide. Software. This is Noelia. She's in the teaser movie. She talks about stay comfortable and continue to use your favorite software while improving your imaging experience. So what did she mean with this? Next slide shows that we have an API available, which some of the software companies have integrated into their system. You know, integrate the API is kind of easy. Our API is free of charge. We want to keep the API same for all products. So the API for RCM1 and 2 is the same. And this is a strategy we also want to keep for the future. That the software companies that have integrated our product, they will be able to work with all our products. Okay. Then the next line is we have designed a unique hardware triggering concept, which is really new. Our strategy is that we plan to work in most of the software packages, open source and commercial. Okay, so this is something in preparation. On the next slide, I will give you one example. Here you can see, this is the RCM2. This is Nikon Nice Elements software. With 100x magnification, we did a 4x4 mosaic, multiple colors stitched in 3D. Okay, but please understand that there is no driver for RCM2 inside NIS Elements. We have a unique way of hardware triggering, which allows us to do this typical imaging inside NIS Elements software, inside Zen software, inside LASEC software, inside CellSense software. Okay, we are still, let's say, finalizing our development. But already in the Nikon Nice Elements, you can see that it will work. I think it's truly unique. Next slide, please. Okay. So a little bit about the benefits. Just a recap. You can see we can work in up to the infrared. We can use always the best cameras available, and by choosing the camera, we always are the most sensitive system, most sensitive confocal system in the market. Okay, highest QE. Next slide. So this sensitivity gives us super resolution at 50 nanowatt. But our system is robust, easy to use. We are flexible in software, and the whole system is versatile because we can work with different kind of laser boxes, different kind of cameras. So we can convert your existing research microscope with RCM technology. So you can get RCM technology built on your research microscope. Next slide. So look at this, the sharpness and precision of super resolution. Compare this with electron microscopy. RCM works with fluorescent images, easy to prepare, very fast, and we don't need to do averaging. RCM is so sensitive that you don't need to do any averaging. Next slide, please. Okay, so this is about an example of why 40x 1.4, why more biology is useful, or is going to help you a lot, because on the left side is the 100x image, and we struggle always to find one mitosis. You need to be lucky in your small view field if you have one mitosis happening. But on the right side, you can see the big field of view allows you to see multiple mitosis at the same time. Really, really amazing. Look at that large field of view image. And Jeroen is now going to play some more examples of the large field of view. Look at this large field of view. Look at this resolution. Oh, this is another example. Multiple cells, all living happily, a large field of view. Okay, next slide. Okay, I always call it the chromosome spread. In one webinar, one participant corrected me, but let me call it the chromosome spread. On the left side, you can see the Olympus 40x 1.4 image, huge field of view. You can zoom it in, and you can zoom down. The digital information, the optical information is there. So in the digital work, then you can zoom in. And if we zoom in on the next slide, you can see the deconvolution. You can see on the left side, the raw 170 nanometer image, and on the right side, you can see the deconvolved, this time with microvolution, 120 nanometer resolution. So please realize that in the whole the whole image, you can see this 120 nanometer resolution. This is just a zoomed out part. Okay, next slide. So this is our team. Go sharper, brighter, and bigger. Get sharp and high contrast images without averaging. Don't miss what is happening, because with the 40x 1.4, you have a large field of view. And get more relevant results by imaging without photo bleaching and phototoxicity effects. This is what RCM2 means. And I believe this is the time that I say bye-bye for you. You can see me later back in the questions and answers. Now it's time for you. Thank you.
Thank you, Peter. Yeah, it's truly amazing. There's kind of no more trade-off now. You can get high resolution, high sensitivity, big field of view, everything in one. So it's I really like it. Anyway, this is to Jeroen now. Jeroen, can you give us a nice demo of the RCM2?
I'll do my best. Sure.
Cool.
So thanks a lot for the introduction, and thanks, Peter, for giving the presentation. I just included this slide to give you a brief summary of what I will be using during the demo. So you can see here is an Olympus IX83 frame. We have in the back, you cannot see it in this picture, but there's a cool LED wide field illumination unit. And then here we have the RCM2, what you have been coming for today. So that we have attached within the Olympus IX83 body, we find two objective lenses that I will use. The 100x 1.5, which is also a very nice objective to get very high resolution images, and the 40x 1.4. So that one is slightly lower NA, but a much bigger field of view. Now, what I wanted to demonstrate with this during this demonstration is this resolution throughout the field of view that Peter also showed in his presentation. So you're going to witness that live. I will start sharing my screen here. So you should be able to see my desktop. I'll be using Micromanager for the demo. As you know, or as Peter explained, we have an API which works within Micromanager, and that API is also being used in other softwares, like, for example, Velocity. They also work with the same API. Okay, so briefly on Micromanager, here we have a couple of buttons for snapping an image, streaming live images from the camera, and multidimensional acquisition, which I will go in later. And then if we move to the right, we can see here the controls for the system. So first of all, I made some binning options for the camera, since this is a camera that uses a lot of pixels. So at 100x, we could apply some binning if needed. And then here is my channel selection. So you can see we have I integrated 2 bypass channels, and we have 3 RCM channels here. Then field of view selection. So I just made a couple of presets here that allow you to scan a smaller field of view for faster acquisitions, or just the entire chip to get the biggest images out. So let's start by focusing in the bypass channel. If I go live, you should be able to see a live feed from the camera. And this is a 100x objective. So it doesn't give you a huge field of view, but it does give you high resolution. I'll be zooming in a bit here. So here you can see the well-known chromosome spread, or synoptonemal complex, which obviously is not resolvable in wide field. So to get a good image, we would have to move into RCM. And I simply can press snap image now. That should generate a high resolution RCM image. There we go. So now we can see we are able to resolve this this very precise structure, and I'll play a little bit with the lookup table so that you can have a good look at home. So here's this synoptonemal complex, and as you can see, there's kind of a spacing in between these chromosomes, and the spacing is really is smaller than the diffraction limit. So a wide field microscope will not be able to resolve this structure. Now, this is a 100x magnified image. What I wanted to do next is move over to the 40x magnification, and then show you that we can achieve the same resolution, but with a much wider field of view. So now I'll move to the 40x and move again in bypass mode and go live. So here we go. I'll be focusing on the specimen. And as you can see, there's clearly much more biology to be studied here. So really you get to see much more biology, but at the same resolution. That's the big point that we want to make here. So here are the same chromosomes that I had in the 100x field in wide field mode. So this is not super resolution yet. So let's take this image as a reference and go again in RCM mode. And from here I can simply go ahead again and click the snap image function. This will now scan this entire field of view and sample that in high resolution. If we then take, oh, here we go, that's already done. So there you go. You can see, if you watch closely, you'll be able to see that we can still resolve these chromosome structures even at this low objective magnification. So this is again very much digitally zoomed in, but we can zoom out and then look at that. There's much more to be studied here. All within the same amount of time as it would take for a 100x magnification image. So we get a much wider field of view. From here, I can build a Z-stack. And what I wanted to show you next is that we can take that Z-stack into deconvolution to generate an even higher resolution image. So I will go ahead and acquire this Z-stack. It will be 1.4 microns in total with 200 nanometer steps. Will take a bit of time to generate. And once that is done, I can save the data and we can go in Micromanager, which is the deconvolution software I'll be using, and show you that we can really improve the image quality even further. So, and this is all also possible due to the ever increasing complexity of cameras. So this camera really has a huge amount of pixels. I'm scanning here over 16 megapixels. The image pixels are tiny, they're 2.5 micron. So that means they're suitable for these lower magnifications. Here we go, this data is saved. So I will save the data, chromosomes 40x 1.4. Data is saved. I can go into Fiji, which is the program from which I will run the deconvolution software. I'll load my image and run Micromanager here. Oops, gives me an exception here. Oh, I think it's still open in Micromanager. So just give me a second. I needed to restart Fiji because Micromanager license was blocked. There we go. So within Micromanager, you simply have to tell what are the number of iterations for the deconvolution that you want to do and the background value that you want to subtract. Now we could do a quick measurement here and see that we have around, well, let's subtract 700 this time. It should give us a nice signal to noise ratio. And then you can see here on the right hand side the parameters for the point spread function. So 40 nanometer pixels is what it reads from the file, 200 nanometer per slice, and then the objective specifications plus the sample specification. Then you can see here that there are loads of other microscope modalities of which you can choose. Okay, so this is not only for rescan confocal microscopy, but you can also use it to deconvolve spinning disk or other confocal data. Then this one. I think to save some time, I will just crop this image right here, because I don't want to be deconvolving that large number of pixels. So this should give me a fairly fast deconvolution. You see, that's like a few milliseconds only. Now we can see that really are able to resolve with very high precision this chromosome structure. And if you would do measurements here, you will find that it indeed is a 120 nanometer resolution that you have here. Here I wanted to stop and well, thanks for your attention. If there are any questions, I'm happy to answer them.
Thank you, Jeroen. And I have a first comment. Actually, we could see that you were so much brighter in 40x because you had to adjust the lookup table.
Yeah.
I think you had 1,000 count for 100x, and you had to go to 1,600 or something like that. So, so very nice. We, as of right now, we have one question for Mike. So if you have any other questions, feel free to write them down. This is now. Mike was asking if the 220 by 220 microns field of view was with 40x, and yes, it's with 40x. With a regular CMOS camera, right, with a 2K by 2K CMOS camera with 6.5 micron pixel size. This would give us 220 by 220 microns.
Yeah, this is actually the camera that I used here is actually much smaller pixels. So it's not a 6.5, but it's a 2.5 micron pixel. It's like the PCO Edge 26.
Okay. Mike is also asking what is the max FPS for a full field of view?
Yeah, it's a very good question, Mike. So that's for a full field of view, we take around 6 seconds to scan. And the nice thing is it doesn't take longer to scan a 40x 1.4 image compared to a 100x 1.4 image. So the scan time is the same. In a regular confocal microscope, you would have to do lots of pixels and adjust the pixel dwell time. Here, due to the much more sensitive CMOS detector, we don't have to do these things, and we can scan this really big field of view in the same time. And then there's another question I see. If I use that PCO 20, that's yeah. This you're completely right. So you can even sample a larger field of view. So the 220 by 220 micrometers is the field of view that is specified for super resolution. Now, what you can do with RCM, you can tell not to do the rescanning twice, but scan it on the same area. And that doesn't give you a super resolution image. It gives you a regular confocal image, confocal resolution image, but it will increase your field of view even further.
Maybe I can add, this was the scene 1 in my presentation. The 14th, the first scene 1, where the image size of the scanner and the rescanner are same.
Correct.
Okay. So then it's a confocal resolution, and then you can get the larger field of view. And maybe I want to add something about the digital scanners. If you compare that to the analog scanners, if you go full field of view, they are a little bit slower. Okay. But if you go to the smaller field of views, then they go faster. So at 512 by 512, the digital scanner is 2 times faster than the analog scanner.
Perfect. Do we have any other questions?
I think just a remark from Mike that it's he didn't realize that it was possible to do a single sweep scan, but yes, we can do that. It's actually similar to the digital zoom that you have in a regular confocal microscope. So in this way, we can play with the field of view and the pixel size. So that's cool.
Yeah, you increase the field of view at the cost of resolution.
Correct.
So okay, I'm getting some pricing requests. Maybe you should address that not to me, but to Vincent.
Yeah, I'll get back to Thomas.
Okay.
Okay, well, if we don't have any other questions, I think we will stop the webinar. Thank you all for being here. Thank you for your questions. Thank you, Mike.
Thank you very much.
Okay.
Okay, thank you so much.
Have a good day.
Have a good day.
Bye, everybody. Bye-bye.
Bye.